Today we're going to look at a 5-bit flash converter circuit using 1, 2, 3, 4, 5, 741 op amps. So I have coming in here, because it requires a dual supply, I have coming in here a negative supply right here, which is in the green wire. That's negative 12 volts plus 12 volts here. And then a DC ground over here. So 3 power connections. We'll have a look at that in just a minute, but before that, let's go ahead through the circuit. The first thing we have is a voltage divider, and the voltage divider establishes the range of the conversion. And then down here we have another voltage divider. In this case, it consists of a couple of resistors that I needed to put together to get a specific value, and a light sensor at the very bottom down here. I don't know if you can see that or not, but there's a light sensor down at the very bottom here. So it measures the amount of light that hits it and turns that into a resistance. When we put that into a voltage divider, that of course then generates a voltage, and the voltage is related to the amount of light. So what we do over here with our op amps is we compare that voltage with the voltage that we get as a reference with our little voltage divider ladder here. These are all 1K resistors. So they divide the voltage at the top equally down to individual voltages which relate to specific amounts of light that hit the light sensor. So the amount of light that's on the light sensor is constantly being compared to a reference voltage for each op amp. That gives us, basically, if we were looking at this in a digital, with a digital brain, we would say that this is a 5-bit converter. It has 5 lights, and each light represents a certain amount of light hitting this sensor. So as we take a cap or something like this and cover up the sensor, what we'll see is that the lights will start to go off as we cover the sensor up more and more. And of course, I'm using a cap that's a little bit clear. I'm going to see if I can go find one that's not, so I'm going to pause this for just a second. Okay, here is the circuit that we looked at over there that measures the amount of light hitting a sensor. Here's the sensor. This is basically a variable resistance, where the resistance is determined by the amount of light that's hitting it. We have that working with a variable resistor, an actual potentiometer, that over there was replaced with the actual resistance that worked for us. So in the initial design, we use a potentiometer here to tune this circuit so that it works with the amount of light in this room. So that generates a voltage at the middle of a voltage divider that is dependent on the amount of light that is hitting that sensor. So the more light that hits the sensor, the less its resistance, the lower the voltage is going to be. Okay? Now, on this side, we have a 12-volt source with a voltage divider. Each one of these is represented by potentiometers, although we've used fixed resistors over there. If we really wanted to tune this, we would make sure, again, that we're able to offset those 10% variations. When we do that, what we end up with is equal voltages at each point here, or equally spaced voltages at each point. These are our reference voltages. So when the signal here, based on the amount of light, gets to 0 volts and exceeds 0 volts, then this LED will come on. When the voltage on the red line climbs and exceeds 2 volts, the positive terminal then dominates. The output will go positive. That will turn this LED on as well. So as the voltage increases here, what happens? Well, the voltage increases and it satisfies or exceeds more of the reference voltages and turns more lights on. Okay? Simple, just an LED and a 180 ohm resistor in series to make sure we're not letting the smoke out of the LEDs, and plus and minus 12 for our source. Other than that, it's a fairly simple circuit. You'll notice that I have written in green here that we have a range adjustment I've already done the adjustments on the circuit and replaced them with their equivalent resistances, but if we were to sell this or use this somewhere else, we'd want to keep that potentiometer in there, use a range adjustment. That basically tells me what's my range of light going to be. If I have that set up right now so that the amount of light in the room here turns on all the LEDs, what's going to happen when I blast it with a flashlight? I've already saturated the circuit. So this allows me to change the range of light levels that will excite this thing from 0 all the way up to maximum. So I need to be able to work within a certain range of lights. Another example is if I had less house lights, then the full amount of light would not turn all of the lights on. So I would want to make an adjustment there as well. Over here, this potentiometer, again over there it's replaced with 2 resistors, is our offset adjustment. Once we've established what the range is, then we need to be able to adjust the offset so that at the very low end all of the lights are on, and at the very high end of the amount of light, I'm represented that backwards. At the minimum amount of light, all of the lights are off, and at the maximum amount of light, all of the lights are on, like the circuit works over there. Now we set ours just a little bit off. If you remember when we looked at the circuit, we set our range just a little bit smaller so that the one LED would stay on all the time. That one LED staying on all the time is what we would then call a pilot LED. It just indicates, if you're in the dark, it would indicate where the gauge is located if it's in a panel, so that you would know that you were looking at it and that it was actually on and functioning. So that would be this one. We're never going to have a situation where this resistance is going to be exactly 0 ohms. Therefore, we're never going to have a situation where we're going to have exactly 0 volts here. In other words, this point will never actually be connected to ground, which means that if I set my reference to 0 volts, then I can never turn this light off. Okay? If I want to be able to turn that light off, then all that would require would be a small value of resistance here, maybe 100 ohms, to put this at 0.1 volts instead of 0. That then would turn this light off when I had no light impinging on the on here. And of course I would probably set that up with a potentiometer as well, so I could fine-tune that as well and make sure everything is as accurate as possible. So the end result of this would be a bar graph. We could do it with square LEDs, like so, and as the amount of light increases, you get an increase in the length of the line. Okay? So a very simple circuit. This is a very commonly used circuit. One of the things about it is that it is very fast. In other words, all of these op amps are working in parallel with each other, so the only delay that you have between input and output is the processing time that the op amp takes to do its job. That's why we refer to this as a flash converter. The downside to a flash converter is that all of these op amps are on all the time, so it uses a fair amount of current. Also, when you start to use larger bit counts, you start to work with 16-bit words and 32 and 64-bit numbers. This can get pretty expensive because you need an op amp for each bit. In binary, or in digital, this would represent a 5-bit analog to digital converter. You can come in, I'm just making a thing, talking about this circuit. So that is pretty much how this works. You'll notice in blue that I've written down some other values of resistance here in relationships of 10. So 1K, 10K, 100K, 1 meg, 10 megs, so on and so forth. If I were to replace my resistors with that, then I would get a logarithmic relationship between input and output, and then I would see, I would be able to represent these as decibels if we were talking about sound, or working with very large ranges of light, I would be able to compress that data and it would make a lot more sense. we've talked about logarithms before. So there you are, a flash converter circuit using 5 op amps, 5 bits. It measures the amount of light hitting the signal, or hitting on this sensor, and then sends a signal out which is compared to a reference. And that gives us a stair-stepping of light levels at our outputs that is dependent on the amount of light hitting the sensor. Later.